Hi everybody and welcome to our new video called Virtual Champions. Let's begin. We hope you enjoy it and like it. Don't forget to subscribe to our channel. First of all, let's remember that our team is made up by María García, Bertha Lozano, Marisol Romo, and Daniela Schaar. Well, in this video we will work with the French football league called Ligue 1, or if we say it in French, is the Ligue 1. First, we'll look up for some statistics such as total matches, minimum goals, maximum goals, and average goals per match to have an idea about how the championship evolves. Now, we did a table to see the frequency of each goal count, and also we create a histogram. As we can see, the minimum goals were 0, the maximum were 8, the total goals were 1049, the total matches were 380, and the average goals per match were 2.76. As you can see, the histogram and the frequency are on screen right now. Well, this tournament can be described with a binomial distribution with parameters n, p, where the k is from 0 up to n. Then, the capital letter N is a binomial random variable that counts the number of goals that are recorded in the score. The little n is the time of a match, that is 90 minutes, and p the probability of seeing a goal during 1 minute. The tables we did before give us the idea of counting the goals in a match. But the question is, what is a counting process? Well, let 0 less than t or equal and t less than or equal to 1, an instant in time, and capital letter nt be the number of goals scored until moment t of a football match. The sequence of random variables is a counting process if it satisfies the following properties: first, second, third, and fourth.
Now that we know what a counting process is, and with the statistics we talked about before, we can compute the probability of registering a goal in any minute. We do this by dividing the average of goals per match by the number of minutes in a match, which is 90, and this is what we get. Then we can use this probability to approximate the distribution goals by means of a binomial distribution, which we also talked about before, with 90 trials of a minute each. Let's say that this random variable n follows the binomial law with parameters 90, and with this result we got, which is 0.03066. These are the results we got, and we can also see a graph here. N1 is the number of goals scored throughout the entire match, so N1 over 90 is the number of goals scored throughout the first minute. Unfortunately, the binomial method has a limitation, which is considering only 1 goal per minute. To fix this restriction, we'll use a Poisson process. But what is a Poisson process? A counting process is a Poisson process with intensity or rate of lambda larger than 0 if n of 0 equals 0. The number of goals scored in different intervals are pairwise independent. The distributions of nt plus s minus nt for all t equal or larger than 0 are equal. The probability that a single goal is scored in an infinitely small interval of size h is this, and the probability that at least 2 goals are scored in an infinitely small interval of size h is around 0. Now we can define the Poisson's limit law by using the fact that the exponential function can be expressed as the limit of a binomial raised to the nth power. We will use this fact for this theorem. Now here we can see how the mass function of a Poisson random variable looks like. Using this, we get these results. And here we have a graph that compares all 3 graphs, the empiric, the binomial, and the Poisson.
In addition, we're going to keep in mind that for a Poisson, We will consider tau 1 as the time elapsed until the first goal is scored, and tau I as the time elapsed between the I minus 1th and the ith goals for I equals 2, 3, etc. So we are going to call this sequence as a sequence of times of arrival. Now let's take a look to theorem A, which says that the random variable tau I is such that the probability that tau I is lower or equal t is equal to 1 minus the exponential function of minus lambda times t for I equals 1, 2, etc. And it is independent for tau j for I different j and j equals 1, 2, etc. Geometrically, it looks like this. Now, with this idea, we can easily simulate goals. Let's take, for example, two teams of this league, Paris Saint-Germain and Lille. We compile the following table. We will use the theorem A to generate the first n goals and their times arrival. Let U be a uniform random variable that takes value between 0 and 1, including the 0 and 1. For some continuous and invertible distribution function f, the random variable x equals the inverse function of f evaluated in U has distribution f. We will use this in Excel for our simulation. Let's go to Excel.
So here it is, our Poisson generator function, which receives lambda as a parameter. And we generate a uniform random variable on 0, 1. And we have a continuous and invertible distribution function f. We have p, that will be the exponential of lambda negative. And while this uniform is bigger or equal to this function, we will repeat this process that will generate our Poisson that we are going to give back with this function. So in order to calculate the lambdas needed for this Poisson, we are going to calculate the mean of the goals scored by PSG as host, and we can see that this is the number of goals that they did at home divided by the matches at home plus the goals against away that the other team got by the matches divided by the matches away, and this multiplied each one by 0.5. And for the guests, in this case Lille, we are going to divide the goals against at home that the PSG gets divided by the matches at home plus the goals for away that Lille did divided by the matches away, and both multiplied by the 0.5. So this means that it is reasonable to assume that PSG will score a mean of 1.47 goals in a direct match when they are the hosts against Lille. And likewise, we assume that the lambda for Lille as a guest will be 1.31. So we do the same when Lille is host. How many goals will the PSG score and how many goals will the host Lille score? And using the function we just programmed with these results, these lambdas, we simulate the results of the match when each team is the host. So we do the function was with this parameter, this one and this one, and we can see we get this possible outcome. But of course, every time we do a different one, we're going to get different results, as we can see here. So one simulation is not sufficient to forecast the result because, as we can see, sometimes PSG wins, sometimes Lille, sometimes they are in tie, or maybe a lot of points are scored by PSG and none for Lille. So this is not at all correct. So we will now use the weak law of large numbers to simulate the result of the match between these two teams. So let's refresh our memory on this law that takes advantage of really large samples.
We'll see the theorem of the weak law of large numbers, or the golden theorem, or also known as the Bernoulli's theorem. Let I1, I2, etc. be a sequence of independent and identical distributed random variables with common mean mu, and In equals to the sum of I1 up to In divided by n. Then, for any fixed positive number epsilon, we have that the limit when n tends to infinity of the probability of the absolute value of In minus mu is larger than epsilon equals to 0. This means that the average of the great amount of simulations tends to behave like the actual average of the corresponding random variable. So let's simulate the match between Paris Saint-Germain and Lille a large number of times and calculate the average of the outcomes.
So now we do a lot of simulations. To be more precise, 15,937 simulations about this possible match when PSG is the host and when Lille is the host, and the matches between these two teams. So here in the outcome, we're going to write which team is the winner or if it's a tie. So if this one is bigger than this one, then PSG won. If Lille has more goals than PSG, then Lille won. And if they are the same, there's a tie. So here are all the possible outcomes here again. And then what we do is do this little table where we write the frequencies of each outcome. So the PSG won this number of times, Lille won this number of times, and there was a tie this number of times. So we then calculate, the same here when Lille is host. We then calculate the probability that each team wins. And this technique is widely known as the Monte Carlo simulation technique because it divides the number of the simulations that got this one divided by the total simulations. So the probability that the PSG wins in a match against Lille in its own house is 42.24%. And actually, when it's also against Lille, it has more probability of winning. And these are all the outcomes.
We can use it to simulate the tournaments. For this, we will assign 3 points to the winner, 1 point if there is a tie, and 0 points for the loser.
Now that we know how the points in the tournament work, we can see that the average points that each team will get when Lille is hosting will be this. And likewise, the average point of each team when PSG is hosting will be this. With this technique, there is no guarantee that the number of points will be an integer number. It will be a number between 0 and 3.
So, in order to get the points that each team will get in a match, we are going to use this function that will receive the lambda of the host, then the lambda of the guest, and the number of simulations that this process will be repeated. So, A wins will be the times that the host wins, B wins the time that the guest wins, and tie when there's a tie. So we're going to repeat this a lot of times, and A and B will do the plus that we already programmed. So they're going to give us an outcome. So if A equals B, then there's going to be a tie. So to this counter, we add 1. If A is lower than B, this means that B wins, so we add 1. And in the other case, that means that A won, so we add 1. So we're going to divide the number of times that A won by the times of the simulation, like we did in the Excel sheet. This is the Monte Carlo simulation. The same with the wins that of B, and the same with the ties. So we're going to create this arrange that will save in the first entry the points that the host gets, 3 times the times they win, by plus the tie. And in the second entry, the times that B wins times 3 plus the tie. And the results will be the following. Here we get, if PSG is the host, the average points that the PSG is going to get is 1.41, and the average points Lille is going to get is 1.28. And if Lille is the host, this team will get 1.13 points against the PSG, and the PSG will get 1.62 points against Lille.
In real life, it may be complicated to compute thousands of simulations per match in a regular season. So the next code solves this problem, using the necessary steps for computing the average number of points that the teams will obtain when one team hosts the other.
Now we want to simulate the whole league to see who is going to be the winner. So we're going to do this table where we wrote the matches at home, goals for at home, goals against at home, matches away, goals for away, goals against away of each team. So with this information, we're going to do the same that we did with the Paris Saint-Germain and Lille, but doing it each team against each other team. So the first thing we need is the lambdas, no? So the mean of goals that the host scores against guest, imagining this one is the host and these ones are the guest. How many goals would this team score against this one? And these are the results. And if this one was the guest and this one is the host, how many goals on average did it score? So for this, we'd use a function called hosts, and for this one, a function called guests. This is what those functions have. So for the host one, we do the same that we did earlier. We multiply 0.5 by the times the number of goals for at home divided by the matches at home of this team, and we add the goals against away divided by the matches away. So this is going to be for the first team playing against the other 20 teams, we're going to get that results. Then number team 2 playing against the other teams, team 3, etc. And the same for the guests. Now we do what we did for the guests, that we also multiply 0.5 by the goals against at home divided by the matches at home, plus the goals for away divided by the matches away. And with that, we got the matrices that I already showed you. Now, with these lambdas, we want to simulate our Poisson many times so we can get the result and then calculate the points that each team gets to see who is the winner of the league. So for this thing, we have this matrix, this program to get the matrix. So this is going to do the same, the host and guest that we did earlier, but it's not going to print it, it's just going to save it there. And what it's going to do is that for every match, we are going to use the AMP function that we used before, that it receives the host lambda and the guest lambda and the number of simulations, 10,000 in this case. So the points that the team A will get, it will be printed in the host's points matrix, and the points that the guest gets is going to be printed in the guest matrix. So here are the results of this function. Here are the average points that the host scores against the guest. So when, for example, I don't know, Monaco plays against Lyon, these are the points that Monaco is going to get. But Lyon as a guest will get the following points. Lyon against Monaco, it's this one, it's going to get these points. So we make a sum of all the points that each one gets as host and the points that each one gets as guest. So we have here this table where points as hosts, points as guests, and the total points. So according to our simulation, PSG is supposed to win, second place for Lille, and third place for Lyon. So we can also sort them by the points, I don't know, as guests, we see that actually it stays the same, but as hosts, maybe it changes the first three. Yes, Lille got to fourth, and Monaco is now in second place. So this is our forecast for the League One matches.
Finally, as we can see, the binomial distribution can be a way to achieve the Poisson process. In this video, we try to present a way to simulate results that goes from taking empiric distributions to the Poisson random process. Then, we use the weak law of large numbers and the Monte Carlo technique using Visual Basic, so we could be able to simulate a football tournament. Once again, we can conclude that it is important and relevant to know what are the applications and how the stochastic processes are used. This specific video was an example of how we can apply the counting process in our daily life. So, Thank you very much for your presence, your attention, and mostly your patience. See you next time.